Cosmology is terrifying. It raises questions. It makes vivid questions that we all have about, what are we doing here? Right?
Yes.
So I try, and I think this goes all the way back to me really being into Carl Sagan. He always used to try this. You try to link it to things that people think about naturally. And that's why people are fascinated by this stuff, because they do actually think about it. It might not be with the right names or the right words or the right facts even, but they're thinking about, how did I get here? How did I come to exist? What is the future? Do we have a future? What was our past? These are universal questions, I think.
How are black holes formed?
They're formed at the end of stars' lives, or at least the smaller ones are. So what happens when a star is burning its fuel, like the sun is now? What's happening is that the sun is carrying out nuclear reactions in the core. They're called nuclear fusion reactions. That releases energy and that keeps the star up. But the star is burning a lot of fuel. The sun is burning 500 or 600 million tons of fuel every second. Hydrogen fuel, converting it into helium. So that can't go on forever. In the sun's case, it'll last for about another 4 or 5 billion years. When it runs out of fuel, then gravity will take over and the star will start to collapse. And if the star's big enough, there's no known force, even the rigidity of matter, that will stop it collapsing. So it collapses and collapses and collapses and forms a black hole. There are black holes, supermassive black holes at the center of galaxies, and we don't fully understand how those form, but they're millions of times the mass of a star. So the Milky Way galaxy's got one. How they form and how galaxies formed in the early universe is a piece of research that's going on now.
So if you remember those amazing, the Gargantua, the black hole in Interstellar, that's a simulation. It's not an artist's impression. It's a simulation of what Einstein's theory tells us a black hole will look like. And so I can use that to talk about what happens when you fall into a black hole. What would you see watching someone fall in? And you can explain all that using Einstein's theory. The idea that it's kind of a well-known idea, it's a bizarre idea that if I was to fall into a black hole and you were watching, you'd never see me fall in. You'd see time slow down, my time slow down as you watch me. So in the end, I'd just slow down and slow down and slow down, and then I get frozen on the event horizon and just fade away as an image, a reddening image on the event horizon. So time passes at different rates as you move close to the black hole and far away, because space and time are distorted by the mass of the black hole.
What is the most likely way that the world could end?
The Earth will end, ultimately, as a cinder, because what's going to happen is that the sun, it'll grow as it gets older, and it'll swell up. It probably won't engulf the Earth, but it'll get close. The Earth will probably drift out because the sun will lose some mass. The Earth will end up toasted as a cinder, probably still orbiting the remains of the sun, which will be what's called a white dwarf star, which is just something that basically fades away. So that's what's going to happen in about 5 billion years. If you mean by the end of the world, you mean the end of civilization. Long before that, we'll have had to escape because the conditions on the planet will not support complex life like us. It'll be too hot. It is impossible to visualize the scale of the universe. In the piece of the universe we can see, there are something like, roughly, 2 trillion galaxies. We haven't counted them all, but that's an estimate based on surveys of the local universe. 2 trillion. 2,000 billion galaxies. And each galaxy is, let's say, around the size of the Milky Way. Some are bigger, some are smaller, but the Milky Way has 400 billion stars in it. It takes light over 100,000 years to cross a galaxy. And there are 2 trillion of them in the piece of the universe we can see. And we're very sure that that piece that we can see is a small bit of what may be an infinite universe beyond. We don't know, actually. And I always say, don't get worried about that, because nobody can picture it.
And they find these unexpected particles. Then what happens?
So we want to know with a Higgs particle, we know what it does, which is it gives mass to everything. So it's fundamentally the thing that gives mass to all the other things in the universe at the most fundamental level. So electrons, for example, and the up and down quarks, they get their mass from their interaction with the Higgs. That's why they're massive. That's another reason we exist. We go right back. We wouldn't exist if there wasn't mass in the universe. And the Higgs is ultimately responsible for that mass.
I keep caveating it because then you get other sorts of mass that are generated, but that the fundamental basic seed, as it were, is from the Higgs. So what we want to know is how that thing behaves, and so you want to study it. So you want to make a lot of them, so you can take a lot of pictures of it and study it a lot and see exactly how it does that. And so that's what we're doing. That's what we're engaged in at the moment. We're making high precision measurements of the way that particle behaves, so we can understand the laws of nature. I mean, that is the laws of nature. How are those particles behaving, and what are they doing?
But it is possible that some new form of particle, something else, could be discovered.
Yeah,
that we don't know about yet.
Because we almost know that there are other particles out there in the universe.
We almost know?
So a thing called dark matter.
Yes.
So we look out into the universe and we see that there's a lot of stuff there that's interacting gravitationally, but is not interacting strongly with the matter out of which we are made and the stars are made. So it's almost certain that that's some form of particle that fits beautifully. And we see lots of different observations of the way galaxies rotate and interact, and even that oldest light in the universe, the so-called cosmic microwave background radiation, we see the signature of that stuff in that light as well. So we think that there's some other particle out there. And to be honest, we thought we would have detected it, I think, at LHC. We have lots of theories called supersymmetric theories that make predictions for all sorts of different particles that would interact weakly with normal matter. Yeah, I think it's broadly seen as a surprise that we haven't seen them at LHC. So that just may well mean that either they're a bit too massive, so we need more energy to make them, and we just haven't quite got enough, or we're not making enough of them often enough to see them, which is one of the reasons we're upgrading the LHC. So we also look for them, by the way, directly. So we have experiments under mountains. We bury them under mountains so the cosmic rays from space don't interfere with them. And we're looking for the rare occasions when these dark matter particles bump into the particles of matter in the detector. Because the idea would be this room's full of them. I mean, the galaxy is swimming with dark matter as far as we can tell, but it interacts very weakly with this matter, so it doesn't bump into us very often. So we're looking for the direct detection of it, and we're looking to make those particles at LHC.
So it's everywhere, but it doesn't interact with us.
Very weakly. So it interacts through gravity, and the archetypal particle that's everywhere that doesn't interact strongly is a neutrino. So we do know about neutrinos. We've detected those, and there are something like 60 billion per centimetre squared per second passing through your head now from the sun. So they get made in nuclear reactions in the sun, but they go straight through your head and actually straight through the Earth, pretty much. Occasionally one of them bumps into something, and we can detect those because there are so many of them. Our universe could well be infinite. We're sure it exists far beyond the bit we can see. So why would I say that? Well, if you think about it, the universe has been around for 13.8 billion years. That means that light has only had 13.8 billion years to travel from the bit that we can see to our eye. So we can only see as far as light has had time to travel. But we think there's a lot beyond that because of measurements we've made of how the universe is curved and what the structure of the universe is. So it undoubtedly extends beyond the little bubble that we can see. How far it extends, it's another great question, but it could be infinite in extent. How will the universe end? Our best estimate is that it will carry on expanding forever. And the reason I say that is because Brian Schmidt got the Nobel Prize for discovering that the universe is accelerating in its expansion, which is a great mystery, because before that discovery, we thought, well, gravity is always attractive, and so it should be, we've got all these galaxies in the universe, and the universe has been expanding since the Big Bang, and so it should at least be slowing down. And there was even a question as, is there enough matter in it to slow it down so much that it stops and recollapses again? But this new discovery, it's only a decade old or so, that the universe is accelerating in its expansion, suggests that it will continue to accelerate unless some new physics appears that we don't understand, and so it will just continue to expand forever. The galaxy is 100,000 light years across. There are 200 billion star systems in it. It's big.
It's too big.
But that's not. So you could just about perhaps conceive in the far future of beginning to spread out into the Milky Way. You could conceive of that. Given hundreds of thousands of years, right? But then then you go, well, where's the next galaxy? Andromeda.
Right.
It's over 2 million light years away. So the idea that you would get across a distance of 2 million light years with any conceivable technology is, to me, probably, I mean, it takes a light beam to 2 million years. So if you want to talk to someone in Andromeda, it will take 2 million years to get a message out there and 2 million years to get it back. So there's a 4 million round trip. That's the nearest galaxy. So it's big, right? Space, that's the thing. But so you can imagine possibly the Milky Way. It's some chance if there are other civilizations there talking to them. But I think beyond that, I just cannot conceive of how it would be done.
Is this relative, though, in perspective to the single-celled organisms that existed billions of years ago in comparison to us? Do we really think that we're the end-all, be-all, and this is the last stop on the road to evolution? No. Isn't it possible that we get so advanced, if we live to be another billion years, that we can, all these ideas that we have in our head about the laws of space and time and the what particle physicists are trying to figure out and what string theorists are prescribing as far as 15 different dimensions? Is that what you said? That
they change their mind all the time. That's pretty unfair to them. But
well, I want to get into that because I don't understand string theory.
No, I don't know.
But I don't understand what you're saying either.
Well, no, you're right.
But my idea is that if we continue to go on the same path, I mean, isn't it possible that we will achieve some unfathomable level of technological proficiency or of control over matter or of an understanding of the universe at such a deep level that we can violate all these things that we now consider laws, like the laws of...
Yeah, so the laws would have to be approximations to some deeper laws going through. But we only detect, I don't know, 1 or 2 a day.
And the idea is that dark matter encompasses an enormous percentage of the universe.
Yes, it's 5 times as much dark matter than is normal matter. And the number is 25% of the universe. So roughly speaking, about 5% of the universe is normal matter, stars and gas.
25% is dark matter.
Yeah, so 5 is normal matter, about 25 is dark matter, and about 70 is dark energy.
That's the other thing.
The other thing.
About.
Yeah.
Yeah. So what the hell's that?
Don't know. Know what it does. Einstein's theory, which works spectacularly well, says that if you put stuff into the universe, as we said before, then it warps and deforms and stretches. And it very precisely tells you, given the stuff that you put in it, how much does it stretch and how does it stretch. And the measurement we have is how it's stretching. So we observe, the thing we observe is how the universe is expanding and how that expansion rate is changing and how it's changed over time. So we have very precise measurements of that. So then we can use the theory to tell us what's in it, given that we know how it's responding to that stuff. And that's how we discovered dark energy. So we notice that the universe's expansion rate is increasing. So the universe is accelerating in its expansion, which is exactly the opposite of what we thought. And this is in the 1990s that we discovered that. We can work out what sort of stuff and how much of that stuff you need to put in the universe to make that happen. And that's where we get these numbers from.
Was there resistance to that when that was first proposed?
Yeah, one of my friends at Brian Schmidt got the Nobel Prize for that. And I remember I talked to him and he said, he was a postdoc, I think, at the time, so a young researcher. And he was making measurements of supernova, the light from supernova explosions, which are so bright that you can see them, hundreds of millions, billions of light years away. And he noticed that if you look at the data, the light is stretched in the wrong way. So we look at the stretch of light as it travels across the universe, and the universe is expanding. It stretches the light, so it changes the colour. And he noticed that there was a discrepancy, which said that the expansion rate is speeding up. It's been speeding up for, I think something like 7 billion years or so. It's been speeding up. So he thought that he's done something wrong because so he checked it and checked it and checked it, and he couldn't find anything wrong. So he did what a good scientist does, which is he published it so that somebody else could find out what he'd done wrong. And he said that he thought it would be the end of his career. He thought it'd be a laughing stock, and he got the Nobel Prize because he was right. It is stretching.
Wow.
It's a great lesson. It means that if you're sure that you can't see what you've done wrong, then you publish it. Ultimately, we're not trying to be right. We're trying to find out stuff. And so
A good scientist will be really happy if they turn out to be wrong because they've learned something.
Now,
And it's good that he took
Yes.
that path because he got the Nobel Prize.
now, when he received the Nobel Prize and this concept started being discussed, what was the initial reaction to it?
Well, it's interesting because it's allowed in Einstein's theory, and it was in Einstein's original theory. So it's got a name. It's called the cosmological constant, and that's it's just allowed in the equations. Equations strongly suggest that the universe is expanding or contracting and not just sat there. So even before we'd observed anything, Einstein had a theory that suggested that the universe is just not static. And actually, it really strongly suggests that there's a beginning. See that if the universe is stretching today, then it must have been smaller in the past, right? Everything must have been closer together, let's say that. There's a man actually called Georges Lemaitre who worked independently of Einstein, but at the same time in the early 1920s, before we even knew there were other galaxies beyond the Milky Way. And they noticed that the equations suggest the universe might be stretching. And so he wrote to Einstein and said, your theory suggests there was a day without a yesterday. Because he thought if everything's expanding now, then it must have been closer together in the past. And so there might be a time when it was all together. And he was a priest.
Wow.
So he's a Belgian priest. So I wrote about this. Now it's kind of my interpretation of it, but I think that he was more predisposed to accept what the equations were telling him because a beginning, an origin for a priest is really a nice thing because it tells you the creation event.
Yeah.
And Einstein tried to dodge it and put this allowed term into his equation, which is almost the stretchy term, to say, well, if it's all kind of contracting or something, can I put something in to make it stretch a bit to balance it all out so it can be eternal? And you can't make it eternal that way. But he tried it. Then he took it out and called it his biggest blunder.
Taking it out was his biggest blunder.
No, he called putting it in his biggest blunder. Or at least some people think what he'd done was miss the prediction of the Big Bang, really. So by trying to fiddle around to have a static universe that's stable, he missed what the equations were screaming. His own theory was screaming to him, which is that, no, the universe expands or contracts. And he missed it, right? So I think that's probably what he meant by biggest blunder. But in any case, he took it out. And then later, in the 1990s, it turns out that, no, it's there. But it's really small. It's tiny, tiny effect. But it's still dominating the universe now. And it will dominate even more in the future. So we think that we're in a universe that will continue to expand, essentially doubling in size on a fixed timescale, which is about 20 billion years. So we think every 20 billion years into the future, forever, unless something happens, the universe will continue to expand and double in size.
Jeez.
And that's the dark energy that's driving that. But nobody knows what it is. It's one of the cutting edge, massive problems in theoretical physics.
And what is being done to try to get a better grasp of what it is?
I mean, we're making very precise observations of it.
Right.
And it looks like this constant. So it looks like it's basically a number, if you like, in Einstein's equations, and just really simple. So it looks like it's something that's maybe a property of space itself. Don't know. But it looks like a very simple thing that doesn't change over time and just stays there. So it requires theoretical advance as well. And so people are trying very hard to do that.
It's so crazy when you go from Galileo to modern theoretical physics that they're still in the midst of this understanding of what all this stuff is.
Yeah, these are fundamental and difficult problems. And we're talking about the origin and evolution of the universe.
Right.
That's what cosmology is. We keep talking about the stuff in the universe. That's what the LHC studies. It studies how the stuff behaves.
Do you envision a time where you can actually physically measure this and have a real clear understanding of what it is and what its properties
The
are?
dark energy. Well, there are theories, for example, which are probably not right, but they're not necessarily wrong either. There are theories that try to link it to the Higgs particle. So the Higgs particle, which we've discovered and can measure, has some properties that we think the dark energy would need. And also this inflation that I mentioned way back at the start of the universe, it has some of the properties that can do that as well. So there are people who try to link them
So we do have an observation of the Higgs, so we can study that. So are they linked? Don't know. These are big mysteries. Something really profound we don't understand about the way that stuff, in particular the Higgs, actually interacts with space and time. So very naively, the Higgs should blow the universe apart, just very naively. It's loads of energy in a very small amount of space, huge amounts of energy in the Higgs field. But it doesn't do anything apart from give mass to things. It doesn't directly affect space. But everything else that you put in space directly affects it. If I was to guess, I'd say there's some link there. There's something going on, and solving one of them might solve the other two: inflation, Higgs, dark energy, something. I think expansion is good, and I think we will expand, and I think we will expand outwards, because there's not much room left on this planet to expand. That's a whole different idea. It's not about gathering scientific information. It's about a frontier and all the benefits that come from operating as a civilization on a frontier, which we've sort of lost on the Earth because there is no frontier left. And so I like that idea. When you talk about Mars, that's the only place you can go. There is no other planet we can go to other than Mars. You can't go to Jupiter or Saturn. You can't go to Mercury or Venus. So if we want to go somewhere and expand our civilization, it has to be Mars, and everything's there that you need. That's a different thing to saying you want to find out stuff. If we just want to find out stuff, then you send robots.
Essentially what happened before the Big Bang. If you define the Big Bang as the time when the universe was very hot and very dense, our best theory of how the universe got into that state is that there was a time before that, and it's called inflation. So the idea is the universe was, in a sense, cold and empty and expanding extremely fast. And that expansion slowed down and stopped. And the energy that was driving that expansion got dumped into space, heated it up, and made all the particles out of which we're made. And that's what we call the Big Bang. It's a textbook theory called inflation. It made predictions, some of which have been tested. Some incredible predictions, actually, about the way that galaxies are distributed across the sky, because they're not just random. If you look at the galaxies, they're in sort of flows and rivers of galaxies that cross the sky in a pattern called the cosmic web. And inflation predicted that before it was seen, actually. So it's an astonishing idea. That theory has a kind of an extension called eternal inflation, which is that the inflation essentially goes on forever. And it just stops in little patches. So you imagine the fabric of the universe, space-time, stretch. And then it slows down and stops in little patches. And each one of those patches is basically a Big Bang and a universe, of which ours is one. So you end up with this sort of picture of an infinite fractal universe of basically an infinite number of Big Bangs. And that's called the inflationary multiverse. If you say, why is our universe the way that it is? Why are the laws of nature such that life can exist, for example? The answer might be that all possible combinations of all the laws of nature exist in the inflationary multiverse. So then it's not surprising there are universes that permits things like us to exist, because every possible universe exists in the inflationary multiverse.
The Big Bang is an event when space gets very hot and very dense and filled with particles. And that may happen again. Or some of the other theories, there's a theory called eternal inflation, which is a theory that, and it's actually the most popular theory, I think, at the moment, for what happened, for why the Big Bang is the way that it is. Because it's got some very special features, the Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. And there was doubling in size in the most popular of these theories every 10 to the minus 37 seconds, which is 0.00000 with 37 noughts, 1 of a second. So it's an unimaginably fast expansion. And then the idea is that draws to a close, so it quite naturally sort of dies away and the expansion slows down. And all the energy that was taken, that was causing that expansion, sort of gets dumped into space and heats it up and makes particles, and that's what we call the Big Bang. And those theories, the slight extension to those, say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed. And just little patches stop and they're Big Bangs. So you get multiple universes, a multiverse. It's called the inflationary multiverse. and we are in one of those bubbles. And that's one of the more popular theories. You need to know that the Milky Way galaxy has got 200 billion stars. Most of those stars now we know have planetary systems. We estimate there are something like 20 billion Earth-like planets, or potentially Earth-like planets, in the Milky Way galaxy alone. So if you're asking questions about what is my place in the universe, you need to know those things. First of all, it's a framework within which you can think.
When you get to those numbers, when you're talking about trillions and billions and all those zeros, my brain just goes numb.
No scientist can picture that number. I mean, even the small number, 200 billion, which is the number of stars in one galaxy. And then when you say 2 trillion galaxies, I challenge anyone to be able to picture that. But it is the reality that we've observed. Gravity is so weak, it is something like a million times weaker than the other 3 forces of nature, which on that scale are of order the same strength. So you have 3 forces that are very strong, and then one force that is incredibly weak, is so weak that its effects, even at the scale of grains of sugar, are impossible to measure. So we don't know the answer to the question, why is gravity so weak? And it is tremendously difficult to do experiments with gravity. Gravity at the moment, it's eluded a combined description of gravity and other forces has eluded us from a mathematical sense. So string theory is an attempt to do that. So the mathematics is hard, but one of the reasons the mathematics seems to be hard, I think, is because there's no experimental signpost. Our best theory of gravity is Einstein's theory of general relativity from 1915, which is a geometric theory. It's a theory that says that gravity is not really a force. It's a result of space and time being curved by objects, energy or mass. And that's the best framework we have. And the highest precision tests of gravity are done looking at a double pulsar system. So you've got a system there where there are 2 stars, which are stars collapsed to the 10 kilometers across. A star collapsed into the size of a city, spinning around thousands of times a second, orbiting another one doing the same thing. So space and time are curved all over the place in that violent place. And actually, remarkably, the predictions of Einstein's theory, 100-year-old theory, fit perfectly with the observation of that extreme physics. So no one's been able to find a problem with Einstein's theory, let alone find an experimental signpost to a new theory, which is a quantum theory of gravity. The characteristics of black holes, the physics inside black holes, is not understood. We don't know. Our theories don't work. We need what's called a quantum theory of gravity to make progress there. So that's the unification of quantum theory and relativity and general relativity, which is what string theory is an attempt to do, but we don't know whether that's the right theory. So this is the edge of knowledge. So we don't know. So we don't know we don't know how to describe black holes properly. We don't have a theory that's capable of describing. We can describe the edge, so this thing about an event horizon and all that stuff, that works. That's not a problem in Einstein's theory. So the idea that if you have a sufficiently dense object, then there's a region around it out of which light can't escape, because space and time are too curved for light to get out. That's fine. The theory describes that properly. But when you start asking questions about what happens at the centre of a black hole, the singularity, the very idea it's called a singularity tells you there are infinities in the theory. The theory is doing things. It's infinitely dense. It's infinitely small. No, it won't be. We don't have infinities in general in nature, other than perhaps the size of the universe, as you say. But so there's something going on there, but we don't have the physical theory. We don't have the tools to describe it. It's an active area of research. So I don't know is a good answer in science, right? And so speculation's fun, but ultimately, we're talking about a regime of nature, which our current theories are not capable of describing with any authority. And that's the inside of a black hole. So this is a baby picture of the universe. 180,000 years after the Big Bang, the universe became transparent for the first time to light. And that's because it was cooling down. As it was expanding and cooling, then atoms form. And at that moment, very, very quickly, the universe becomes transparent, and so photons of light can travel on through the universe, and they've been doing so ever since. And we can take a photograph of that, and we have done with a series of satellites, the most recent which is called Planck, which is a European satellite that's up there. So this is a baby picture of the universe, as it was 380,000 years after the Big Bang. It's a very beautiful picture. But in explaining that, that's given support to theories called inflationary cosmology theories. So inflationary cosmology theories say that before the universe was hot and dense, which we tend to call the Big Bang. Before that, the universe was still there, and it was doing something else, which was an exponential expansion. So it was expanding exponentially fast, way faster than the speed of light. Then it stops, and all the energy that was causing that expansion gets dumped into space, heats it up, and that's what we see as the particles and energy today. So those theories are kind of interesting. But they also suggest that there are theories called eternal inflation theories that say, well, how long did that period of expansion go on for? And does it all stop at once, or does it stop in patches? And if it stops in patches, if it stops in a little patch, you'd get a Big Bang and a universe. And if it stops in another patch, you get another Big Bang, another universe. So these theories suggest perhaps there are an infinite number, possibly, of Big Bangs, in inverted commas, which would mean there are an infinite number of universes like ours. And they're being created now, all the time, and they will continue to be created forever. So you get this fractal multiverse, ever growing exponentially fast. And really bizarrely, those theories have some support from the cosmic microwave background. They're theories that explain the structures we see. I should just underline the fact that this is speculative in a sense, but it's relatively mainstream. What one of my colleagues noticed, and some physicists have noticed, is if you were some kind of omnipotent deity programmer and you wanted to run what's called a Monte Carlo simulation to say, well, I'll vary the strength of gravity in one universe and vary the mass of the electron in another one and vary these physical constants and see what happens, then this is probably the kind of thing you'd do. This is what it would kind of look like. So that you can make an argument that the universe, in some sense, looks like one of these kind of so-called Monte Carlo simulations, because it gives you the possibility of generating every possible number of different ratios of the strengths of the forces of nature and all these things. But I just have to emphasize, this is way out there, on the edge, but it's fun. And what is fun and interesting, though, is that the wind all the way back, the inflationary cosmology bit is probably the most widely accepted theory at the moment for how the universe got to be the way it is. And it does lend itself to this idea that there may be a multiverse. And it may be that in each different pocket universe, if you like, you can have different physical constants. So most of them wouldn't allow life to exist, but some of them would. So our universe looks very fine-tuned if you look at it, in a sense. It looks like the laws of nature were very slightly different. You wouldn't get carbon, for example, produced in stars in large quantities, which you need in order to, and when the stars die, the carbon and the oxygen come out and they relapse into another generation of stars and solar systems, and that's how you get the heavy elements that make up our bodies. And so all those things you either try and find an explanation for why the laws of nature are the way they are, or you go to one of these multiverse theories and say, well, actually, every possibility occurs in nature. And then we shouldn't be surprised that we live in a universe that seems fine-tuned for life, seems perfect for us to exist in, because every possible combination of the laws of nature exists somewhere. And this is where cosmology is at the moment. This is genuine. You could go onto the web and Google it. You'll find 1,000 review papers on what's called inflationary cosmology. And it is cool and interesting, actually. Infinite numbers of infinite universes. These theories exist. We say the universe began 13.8 billion years ago. That's a measurement. So because we can measure the speed that all the galaxies are flying away from us, essentially. You can run time backwards, if you like, to find out when they were all on top of each other. And so it's quite a simple measurement, and we've done that. So we say the universe began 13.8 billion years ago. But actually, all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence. And that means that actually the universe could have always been eternal. When I talk to people, some people get upset about that. Some people would rather it had a beginning. The idea that it might have been around forever is more frightening somehow than the fact that it began. What terrifies you the most, an eternal universe or a finite universe? If the universe is infinite, which it may well be, in fact, there are many ways the universe can be infinite, then that would happen. If it's in accord with the laws of physics, then it can happen. And everything that can happen in an infinite universe will happen, because the universe is formally infinite. So I contend in an infinite universe, even the most unlikely possibility must happen. In fact, formally, an infinite number of times. It is one of the more widely accepted theories about hominin evolution, as they call it, is that climate change played a key role. And actually, there's in my latest series, Human Universe, we focused on a theory which links the climate change, particularly in the Rift Valley, because we know that the big jumps in brain size all occurred in the Rift Valley of Africa, and it's quite remarkable actually, and that's broadly speaking accepted, I think, although there's a lot of argument with anthropologists because the data is sparse, but it's broadly accepted that. And it seems that the big jumps in brain size occurred at times when the Earth's orbit was most elliptical. So the Earth's orbit oscillates, it becomes more elliptical and more circular, and there are many different oscillations driven by gravitational interaction with the planets, like Jupiter in particular. And it seems like when the Earth's orbit's most elliptical, the rate of climate change in the Rift Valley is higher and more extreme. And it seems to be the case that there's relatively strong evidence for the case that when you get these really rapid times of climate change, then you get increases in hominin brain size, and therefore increases in intelligence. There's a big one 1.8 million years ago, which was a very big increase in the number of species in the Rift Valley, of which Homo erectus was one of them, which eventually led to us, and a big jump in brain size as well. And this was at a time when there's strong evidence for rapid climate change in that region.
So that makes sense, like the adaptability of these animals, experimenting with new food sources, trying out new hunting methods. A lot of them changed from herbivore to omnivore, a lot of the primates that were observed, right?
Well, that's where it gets controversial when you look at the academic research, because sort of Darwinian idea that so you get this pressure from climate change, but then what's the selection effect? Because climate change happens over many generations, it doesn't happen over one generation. So the question is, well, what actually is doing the selecting? What are we selecting for? Why is this group more likely to breed and be more successful if it's more intelligent? So some people say, well, it's because they were forced into groups. So it's group dynamics. It's the fact that you end up with bigger tribes, hundreds of individuals cooperating together, and that's what's being selected for, and you need to be intelligent for that. Some people say, as you said, that it's adaptability. So maybe they have to learn to go fishing, or they have to learn to eat the particular different crops, and then maybe that's
right.
So that's a big area of debate about what might have been the selection pressure, this precise selection pressure. But it does seem pretty nailed down that climate change, certainly in that region of Africa, in Ethiopia and Tanzania and through the Rift Valley, had played a role in driving us towards intelligence. And it's interesting that the time scale is very small, by the way. I mean, so you go back 4 million years, and things like Australopithecus are around, which are basically upright chimpanzees. The brain is not much bigger than a modern-day chimp. But then you go to 200,000 years ago, and that's when Homo sapiens first emerged, just over 200,000 years, which is not very long ago. And it's quite remarkable, actually. And the modern theory is they spread out of Africa about 60,000 years ago, and they made it into Europe about 43,000 years ago or so, into North America and South America only 15,000 years ago. So it's quite a rapid spread. And the fact that we've only been around as a species for at most 250,000 years, 250,000 years is quite remarkable.
We don't have any evidence for alien life is the answer. So in the past, we've landed missions on Mars, for example, the Viking missions in the 1970s.
Do you think time travel will ever be possible?
Not into the past. If you travel at 99.9999999, that's 8/9% the speed of light, to Andromeda, which is 2.5 million light years away, and then turn around and come back again, then for you on the rocket, 100 years will have passed on the round trip journey, but 5 million years will have passed on Earth. So by travelling fast relative to people who are stationary, the clock runs slow relative to theirs. So you can travel into the future, arbitrarily far into someone else's future. But into the past, it's true to say, you know, that Einstein's theory of general relativity, his theory of gravity, allowed you to curve space and time. What I'm talking about there with travelling to Andromeda back is what's called special relativity. So it's flat space and time, and that you definitely cannot go into the past in special relativity if space is flat. If you're allowed to curve space-time, then there are solutions to Einstein's general theory of relativity that allow you to build wormholes, which would allow you in principle to take shortcuts around. So although you can't exceed the speed of light on the surface, it's like going to Australia but going through the Earth rather than going around the edge. I believe most physicists who work on quantum gravity think that there won't be stable wormholes in a quantum theory of gravity, but that's not proved as far as I know.
Because you don't have a proper quantum gravity theory.
Yeah, the thing with travelling to the past is doesn't seem to be the right way to build a universe. And indeed, in general, the universe seems to be built such that you can't do that. Interestingly, though, when I said about the electron that can be anywhere in the universe, it's not only anywhere spatially, it's temporally as well. So in what you do in Feynman's path integral approach is integrate over space-time. So you allow it to do all paths, including paths in the past. Right, that's what the way it works, but they all cancel out. But that seems to be a calculational thing.
If two black holes are next to each other, what would happen?
They'd orbit around each other in the same way planets orbit around the sun. I mean, the black hole is just a thing that has some mass. Let's say it was a black hole, 3 times the mass of the sun, then it behaves gravitationally exactly like a thing 3 times the mass of the sun. People think that black holes, everything just falls into it. But of course, everything doesn't just fall into things. If you turn the sun into a black hole, the Earth would carry on orbiting around it in exactly the same way that it does now.
Of stuff.
Is it? It's just to do with the mass. The fact that light doesn't travel particularly fast over cosmological distances, 186,000 miles a second. That means that as you look out to even nearby objects, let's say the closest object you can see with the naked eye, the Andromeda galaxy, if you look at that, about 2 million light years away, it means you see it as it was 2 million years in the past. You look at more distant galaxies, 10 million light years away, 10 million years in the past, and so on. So you could ask the question, well, in that case, are there objects that are so distant that the light travelling from them began its journey close to the Big Bang itself? Is that possible? And the answer is yes. And that light was first detected in the 1960s. It's called the cosmic microwave background radiation. So essentially the idea is, how far can I look in every direction? You can look about 13.8 billion years into the past, back to the origin of the universe. It's on this diagram here. It says afterglow light pattern, 380,000 years after the Big Bang or so. That is the furthest we can see. We can't see further back than that because in earlier times the universe was so hot and so dense that it was in the form of what's known as a plasma. So essentially the atoms couldn't form. Temperature was too high for atoms to form. So you have electrons and primarily electrically charged protons and helium nuclei buzzing around in a thick soup, opaque to light. But at that moment, and it almost is a moment, cosmologically speaking, 380,000 years after the Big Bang, the universe is expanding and cooling, and it becomes cool enough for atoms to form, and becomes transparent almost in a moment. And so the light can journey across the universe ever since from that point, and we can detect it today. And that's what we call the cosmic microwave background. Here is the most recent photograph of that. So this is presented as a sphere because that's essentially what it is. It's a celestial sphere. So it's as far as you can look in every direction surrounding the Earth. And what you're looking at there is an almost featureless and formless universe. The colours correspond to slightly different temperatures in the light, which are really telling you that there are regions which are very slightly denser than other regions in the early universe, but it's almost uniform to 1 part in 100,000. So we're seeing an almost uniform soup, no stars, no galaxies, no large structures in the universe at all, and that is telling us that the universe has not always been the same as it is today. It is not eternal in the sense that it's not always been around with galaxies and stars and planets. At this point in the past, which we can see in the photograph, there were no stars and no planets and no galaxies. The universe was a hot, dense plasma. And that is essentially the clinching piece of evidence, certainly when it was first seen in the 1960s, that told us that this theoretical prediction that the universe was once very hot and very dense was correct. It matches observation. The universe was hot and dense 13.8 billion years ago. Now, those fluctuations, the different colours, as I said, correspond to very slightly different densities in the early universe. What do they tell us? These are the seeds of the galaxies. So you stick this, essentially you can stick this into a computer simulation, evolve it forward in time, and you will see 13.8 billion years later a distribution of galaxies that matches statistically the distribution we see in the Sloan Digital Sky Survey. Again, so matching observation. So the question becomes, if these little overdense regions collapse to form the stars and galaxies, where did they come from? And this is where we start to probe theories back towards the Big Bang, and in a sense, theories of what may have happened before what we now call the hot Big Bang. So if we define the Big Bang as a time when the universe was very hot and dense, we have a theory which was pioneered by Stephen, amongst others, back in the 1980s, that tells us how, or predicts how, these small areas of different density could have formed. It's a theory called inflation. Before the universe got hot and dense, it was still there and it was doing something else. It was stretching very fast. It was doubling in size on very short time scales, actually around 10 to the minus 37 seconds, which as you write it out on a piece of paper, looks like this. That's why the theory is called inflation, by the way, because the thing is inflating very fast. The idea is that inflation is driven by the stuff that you put in the universe. This is central to Einstein's theory of general relativity. In this case, the stuff is something called an inflaton field. It's the kind of stuff that makes the universe stretch very fast. But what was developed actually here in Cambridge in the 1980s, particularly, was the idea that smooth sort of ocean, if you like, a field filling space, is not entirely smooth. It can't be. It must have ripples in it. It's not really a still ocean of energy. It's like a stormy sea. And what that does for you when you calculate that is it tells you as that inflation draws to a close, as it must. The universe has to stop expanding at this rate and goes through the hot Big Bang. Then some pieces of space will be stretched a little bit more than others because of the ripples in the energy field that's driving the inflation. Some bits of the universe stop inflating a little bit earlier than others, in other words. That leads, when you dump the energy into space and heat it up and make particles, it leads to a slightly non-uniform distribution of particles in the space, which you can calculate from the theory. And when you do that, you find the pattern looks like this, our observation of the universe 380,000 years later. So that's the reason why inflation is, I would say, although there may be a few people who disagree, but I would say it's the most commonly accepted theory of how the universe came to look like that, which subsequently tells us how the universe looks like it does today.
We could go arbitrarily far into the future by flying around in a rocket very close to the speed of light. So we could come back a million years in the future and look at the Earth and find out what had happened. You can't go back as far as we can tell. A way to think about for the satellite navigation system, for example, GPS, the clocks on the satellites tick at a different rate to the clocks on the ground. Over 30,000 nanoseconds per day difference. They're in a weaker gravitational field and they're moving and all sorts of things. Light travels 1 foot per nanosecond. So that's 30,000 feet of position measurement if you drift your clock out by 30,000 nanoseconds. So it's a big effect for when you start using time to measure distance, which is what we do. If you're carrying your watch with you and you go between here and tomorrow, you go this way, you go off and maybe you fly to Dallas and back. Someone else can take a different path, obviously. And so that a different amount of time will pass for them between those two things that happen. It's a tiny amount, unless you travel, someone goes close to the speed of light, or someone goes near a black hole where the space-time is all distorted.
1 in 10 stars in the Milky Way having a potentially Earth-like planet around it. This is one of my favourite photographs of the Milky Way. It's taken from the European Southern Observatory in Chile. In the southern hemisphere, they're fortunate because they're pointing towards the galactic centre. The top of this arc is the centre of our galaxy, obscuring a supermassive black hole, 4 million times the mass of the Sun. We're looking at a galaxy with 200 billion stars or so. We now know that most of those, the overwhelming majority, have solar systems. The estimate for the number of Earth-like planets in that galaxy, that's rocky planets, the right distance from their star to potentially support oceans on the surface, is of order 20 billion. So we're speaking about in terms of 1 in 10 stars in the Milky Way having a potentially Earth-like planet around it. Now, we can't, of course, see the structure of a typical galaxy from within. We have to step outside. And when we step outside and start to look at local galaxies, the scale of the challenge of trying to understand the universe, I think, becomes clear.
How do
If you squashed it down within 3 kilometres of radius, you'd get this kind of distortion in of the black hole in the Milky Way galaxy. We could be falling through that horizon now in this room, and we wouldn't notice anything, except that we couldn't get out again. And ultimately, in a few hours, in that case, time would end for us. So you go to the end of time.
So we wouldn't notice.
Not for the big black holes. We could fall across this horizon. It's just like being in empty space for us. We would just be talking now, and we could have been talking on the outside of the horizon, and by the time I finished the sentence, we could be on the inside of the horizon, inside the black hole. And according to Einstein's theory, at least, which is the theory that predicted them initially, we could just do that. We could just go in, and we wouldn't notice for a bit. The thing we would notice ultimately is you go inexorably, nothing you can do, you go to this thing called the singularity once you've crossed the horizon. And you are going to that thing.